Hello, my name is Mio Ashosh, and today I'll be presenting to you my Physics 2212 Lab 5 Magnetic Molasses. So a little introduction. The purpose of our lab is to study the concept of Faraday's law and electromagnetic induction by simulating how a bar magnet moves through a conductive aluminum tube. And then with this, we examine how the magnetic field, induced current, and forces interact within the system. And we also develop a computational model with GlowScript. And a summary of my main results is that the experimental time was 1.728 seconds, and the computation model came out to be 2.233 seconds. So some of the fundamental physics principles: we have Faraday's law, which describes how changing magnetic flux induces an electromotive force. And then we have Lenz's law, which states that the direction of the induced current opposes the change in magnetic flux. We have the Biot-Savart law, which explains the magnetic field generated by a current-carrying conductor. And then we have Newton's second law, which is force equals mass times acceleration. So our possible errors is that the magnet could collide with the walls of the tube, which may slow down the time. Inaccuracies in timing measurements could affect results. And then we could do the influence of air resistance could also be a possible error, but we're assuming that its air resistance is negligible in this scenario. We also have other assumptions: the uniform conductivity of the aluminum tube across its entire circumference and entire volume. And then we have ideal magnetic dipole, is that the bar magnet is modeled as a perfect point dipole to simplify our calculations. So the system of our experiment was a bar magnet aluminum tube, and then the surroundings were just the external environment and gravity. And then our initial conditions was that the north pole of our magnet was directed downwards, and we determined this by using a compass. And then the magnet starts at the top of the tube, and initial velocity is set to 0. So our procedure, so for part A, we had the setup. We held the aluminum tube upright, and then we dropped the magnet through multiple trials, and then used our phones to record the time and a video. And then we analyzed this. So our experimental values were as follows in the 5 separate trials, with an average time of 1.258 seconds. And there's a picture of me performing this with my lab partners. So here's a little overview of our computational model. We can see on the top left we have our constants, and then we can see the several calculations to get our computational model output. So a little conclusion are what if questions. What if the resistivity of the conductor was reduced as close as possible to 0? How would the dynamics of the falling magnet change? So I think this would significantly enhance the braking force due to a larger induced current as described by Ohm's law, and as a result the magnet would descend more slowly, I think. And then what if the holes or slots were cut into the tube? How would this affect the currents in the model? I think this would interrupt the current flow, and this would reduce the number of current loops. And I do think this would make the magnet fall through the tube much faster. So yeah, thank you.